Now that we have some idea what a limit is, we're going to be computing some limits. First up, they have a theorem for us to look at, a theorem about linear functions. If I think about a linear function, any line, there are no breaks, no jumps, nothing that will cause an issue with a limit. No matter what point I pick, all of those points that are in the neighborhood are all going to be going to the same value. Now the proof for this theorem will come later on in the chapter. So for right now, we are just going to buy this hook, line, and sinker that if we are looking at any linear function, if we would like to know what the limit is, we just plug that value, whatever it is we're looking for the limit of, plug that value into our function and we will get what that limit is. So let's look at a couple of examples. Our first example wants us to compute the limit as x approaches 3 of our f of x. I notice that my f of x is a linear function. Therefore, I can just use my theorem 2.2 and say the limit as x approaches 3 of my f of x is the exact same thing as if I just plugged in a 3. And computing this would be 3 halves minus 7, so that would be like negative 11 halves. The next one, I have a linear function. It's a specific kind of linear function. It is a constant. And that is just y is 6. No matter what, y is 6. Same thing, is still a linear function. It's just a specific kind of one. I can do the same exact thing. I take the limit as x goes to 2 and I plug in a 2, but it doesn't really matter where I'm at. If I'm at 2, 3, 4, or 5, this thing is still 6. And there's the answer to the B part. So they have, for our viewing pleasure and our using pleasure, we are going to get to use these limit laws. Now these limit laws, once again, just like theorem 2.2, we don't get to see the proof of these, but we will later. We don't get to see them right now, but we will get to see them later on. Let's look at what our assumptions are. First up, it says we have a function f of x and g of x. They both exist, and the limit exists at x equal a. So we don't have a condition where we've got some sort of break or something where the neighborhood is not going to a central value. They are going to a central value. And the following properties, c is a real number and m and n are greater than 0. This has to do with when I use a c for law 3 and when I have an n and m, such as for laws 6 and 7. So let's figure out what they're talking about here and then we'll use them. Law 1 says that I have some sort of sum and I would like to know the limit of that complex sum there. So I've got this sum. What they tell me and what you'll be proving later on is that it will just be equal to the limit of each one. So if you have two functions and they're added together, you can break it apart, just find the limit of each one, and that'll be the limit of the, and add them together, and that would be the limit of the total function. And law 2 is similar, but it's just difference. Law 3, if you have a constant multiplied by a function, it will be exactly the same as if you just pull that constant out and then find the limit and multiply those two together. Very similar on the product. You have two functions multiplied together as a unit. You can break those two apart and find the limit of each individual one, and similarly again with the quotient. And also with the power rule, you've got this function raised to a power. What you can do is just find the limit of that function and then raise your limit to that power. and it expands also for fractional powers. However, they do note that m must be even, meaning that your root, it must be an even root on that. So let's work these limit laws and see what we get. All right, the A part. In this A part, I have this unit. To me, I see first up a quotient. I see a numerator and a denominator. So I will be using law 5. So law 5. And with law 5, that says to just take the limit of the numerator and take the limit of the denominator. So I'll write it as such. Limit as x goes to 2 of f of x minus g of x. And then the limit as x goes to 2 of h of x. Now it's very nice that that denominator, I already know what that is. This thing right here is an 8. That's handy. That one's already done. The numerator, this is law 2. So I'm going to use law 2 to break that apart, and that will be the limit as x goes to 2 of f of x minus the limit as x goes to 2 of g of x all over 8. And now I know what the limit of f of x as x goes to 2 is. That is a 4. And this guy, the g of x, is a 5. So I will just crunch those numbers for you. And I get 4 minus 5 is a -1 over 8. And there is your answer to the first problem. Next, I see two chunks here. I see this chunk and I see that chunk. I'm going to break that apart using law 1. So I'll have the limit as x goes to 2 of 6f of x g of x. That's that chunk, plus the limit as x goes to 2 of h of x. Lucky for me, I know what that one is. That one, as I found out before, is an 8. So now all I have to do is use, I've got this guy here, which is a constant multiple. That's law 3 multiplied by this. So I'm actually going to do law 3 and law 4 at the same time. And what that's going to have me do is just multiply the 6 times the limit as x goes to 2 of f of x, breaking apart for the product, and that was law 3. Breaking apart for the product, that is law 4. Limit as x goes to 2 of g of x, all plus 8. Oh, not plus. Times, excuse me. Now I know the answer to the f of x. That one is a 4. This one is a 5. And then I'm just going to crunch these numbers. And if I crunch them, I'll have 6 times 4 times 5 plus 8. And that equals 128. All right, last one. Let's get a new color. Okay, this is just straight up power rule, power law, and the power law says I can take the limit And once I find that limit, just raise it to the third. As such, I know what that limit is. That limit is 5. I'll raise it to the third and I'll get 125. I can expand those laws to include polynomial and rational functions, because if I think about it, a polynomial function is just a combination of sum and maybe some power and a constant multiplier. So I could just combine those laws. That's how the proof would look. Once you proved those laws, the polynomial function would follow, because I would just show, well, now I can combine the sum and the power and the multipliers. The rational function is just an extension of the polynomial function limit, because it's just the quotient. So let's play with some of these and see what we get. Since I have that case, what I can do is, and this tells you here, what this is actually saying, I guess I ought to say what it's saying. If I have the limit of some polynomial, I can just plug that value in for a. So my x is then replaced with an a, and then I just crunch the numbers and see what I get. Same goes for a rational function. Notice that I just plug it in and that's my limit. So I will say 3 times 2 squared minus 4 times 2 all over 5 times 2 quantity cubed minus 36. And just crunching these numbers is, let's see, 12 minus 8 is 4 over 8. 40 minus, that would be a 4. Oh, that guy. All right, so this guy is a 1. There we go. Underline it just for fun. My next one really isn't a rational function. So I'm going to need some of these laws here. The reason it's not a rational function is because of this stuff here. But it'll extend. I'll be able to use my rational function rule, and let's see what we get. I'm going to first use the quotient rule. So I have the limit as x goes to 2, because I can't use the rational or the polynomial quite yet, but just wait. 2x cubed plus 9 plus 3x minus 1. Denominator, limit as x goes to 2 of 4x plus 1. Now, that denominator I can substitute, because this is a linear function. So I can just plug the 2 in there, and I can probably go ahead and let you know what that denominator is. Let's see, 4 times 2 is 8 plus 1. That's going to be a 9 in that bottom. Probably ought to write that out though. 4 times 2 plus 1. The numerator, not quite anything yet, but I see from law 1 that I have the sum of 2 different things. So I'm going to use that. And I'll have limit as x goes to 2 of the square root of 2x cubed plus 9 plus the limit as x goes to 2 of 3x minus 1. Alright, second part I can now substitute in. And this part here, this very first part, I can use this fractional power rule, and I'll be able to plug in from there, because it will then just be a polynomial. So I can plug into each using now for this one I was using theorem 2.2 2.4 or 2.2, whichever one, because you can say that you're using either. And then for this side over here with the fractional power, what I did was I used the fractional power, I used law 7, and then I used theorem 2.4 because what's left is a polynomial once you raise it to a power. So let's plug all of that in. That would be square root of 2 times 2 to the third plus 9, and then plus 3 times 2 minus 1, 8, that would be a 9. And I'll crunch this in my calculator here for just a second. Alright, and I wanted to get those laws written in there for you so that you know what it was I was using. If you crunch this, you get a square root of 25 is 5, and then you'll end up getting plus this value here would be a 5, so then you'd get 10 over 9. We're going to extend this law 7 to include left and right hand limits. So I've got my fractional power here. Notice that I have written that what they've written is this, a plus sign there. Whoops, that's a really crummy arrow, sorry about that. So there's a plus sign there, and that plus sign there means from the right. And this minus sign would then mean, and you guessed it, from the left. So I can look at a limit not just with the entire neighborhood, but I can look at it just totally and specifically from the right and from the left. So let's see what this means. The limit as x approaches 1 from the left of this f of x. So let's go to our graph. From the left, and I want you to take your left hand, and if you take your left hand and you move along the graph, if you learn to do it this way, then you won't get confused whenever you're trying to do your homework and have to keep looking up. The negative sign means pick up your left hand and move your left hand towards that point. And if I move my left hand towards that point, the y's are going to 2. Likewise, if I look at x going to 1 from the right, pick up your right hand and move your right hand towards that point, and it is going towards the value of, and what are the y's? Remember, this is what are the y's. The y value is going to 0. For the limit to exist, those numbers and in the neighborhood around that 2 must all be going to that same, or that 1, sorry, x is going to 1. So must all be going to the same point, and they're going to 2 different points. They're going to, one side's going to a 2 and the other side's going to a 0. That means that this limit, the limit for the whole function going to 1, does not exist. We're going to shorthand that as DNE from here on. Another couple of ways to get limits. I see that this is a rational function, so I should be able to just plug in a 2 and get my answer. However, if you'll notice, if I plug in a 2, 2 squared is 4, minus 4 is 0, and I get a 0 in the denominator, so I don't know what the heck this thing is doing. If that happens, one technique that you might try, and it's a favorite, been a favorite for many years now, you've been doing it a long time, let's factor. And see if something will cancel. If it cancels, great, and if it doesn't, then you'll have to try some other technique. So I'm going to cancel that numerator and denominator, x minus 4, x minus 2, check it, yep, that's it. And the bottom one, x plus 2, x minus 2. since it is a difference of squares, that cancels out, and I get the limit as x goes to 2 of x minus 4 over x plus 2. I can plug it into this puppy. 2 minus 4 over 2 plus 2. That equals negative 2 over 4. My answer is negative 1/2. Cool beans. Da da da. Next, if I try to plug in a 1, once again I get this whole denominator issue. Something that works for me quite often is when I have a square root guy, try multiplying by the conjugate and see if it works. It might work, it might not. I don't really know. So I'm going to multiply here top and bottom by the conjugate. So I'll get the limit as x goes to 1 of multiplying numerator times the denominator, square root of x times square root of x is x. The middle terms, the square root of x times that is square root of x minus the square root of x. Middle terms cancel, and I get x minus 1. I'm not going to multiply out the denominator because, because I got what I wanted, so I'm stopping right there because those two cancel, leaving me with 1. Oops, I got to write limit as x goes to 1 of 1 over square root x plus 1. And I can plug into this one. 1 over square root 1 plus 1 equals 1/2. Dink, 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 dink. Next one. They're wanting you to look at what's going on with the slope of this 2 to the x. Now it seems like this is out of the blue. If you've already been through a calculus class, you understand what they're doing here, but if you don't, it really looks like this is out of the blue. So sorry about this one. I'll just show you what it is they're wanting you to notice. You're looking at a secant line between x and some value that's really getting close to x. So you're trying to get those 2 points to be closer and closer together. So looking at that slope, there between these 2 points, you know, it gets closer and closer. I keep getting closer and closer to this is between 0 and 1, this is between 0 and 0.1, 0 and 0.01. As I keep getting closer and closer, I'm getting closer to this value of 0.6931. And it is not obvious, it is not obvious at all that that happens to be the natural log of 2. So if you were to punch that on your calculator, you will end up seeing that this natural log of 2 is going to exist in our slopes every time we look at some sort of exponential. Whatever our base is, we're going to have, if this had been a 3x, that slope would have been the natural log of 3. If this would have been a 4 raised to the x, it would have been the natural log of 4. And that is not apparent at all, but that is what, for some reason, they're wanting you to look at right now. Next is the Squeeze Theorem. The Squeeze Theorem is used in quite a few proofs. What you have is you have some function g right here, this function g. He is in between two other functions, and that means he is entirely less than h of x, and he's entirely greater than f of x. So here's where they're stating that. Right here, they're saying that g of x is always above f of x and g of x is always below h of x. Okay. Now, if just these two random functions that I chose, one always below and one always above, if they have as their limit at some particular value of a, if they have as their limit the exact same value, and g is always in between, then the limit of g, whether g exists at that point a or not, is irrelevant. The limit of g of x will be L. Now, we're supposed to use the squeeze theorem to confirm the following limits, because if you'll notice, we didn't do any trig functions in our laws that we looked at. So we're going to use the squeeze theorem to kind of prove to ourselves that the limit of sine x is 0. So we'll take our sine x function, and I know that this sine x function is always, sine x function is always below absolute value of x, and the sine function is always above negative absolute value of x. Since, and we're given that right off the bat, so we're given this fact. Now what I need to do is just show that the limit as x goes to 0 of absolute value of x, I can plug in for this because this is the form of a linear function. I can plug in a 0, so this limit equals 0. The limit as x goes to 0 of negative absolute value of x also equals 0. I have this condition right up here, the condition where the limit as x approaches 0 of the function below and the function above both are equaling 0. Then what follows is that the limit as x approaches 0 of sine x must then be 0. Alright. Another case where it's not readily apparent, we're going to look at, this is what we would like to know. We'd like to show that the limit as x approaches 0 of cosine x equals 1. We'd like to show that. We're going to do that not by looking at cosine x, but we're going to look at 1 minus cosine x. And then I promise you we'll get there. So I'm given that 1 minus the cosine x is always in between, so there's my picture of 1 minus cosine x in black. He's always in between the absolute value of x and just the constant function of y equals 0. So let me go ahead and do my two statements of the limit as x goes to 0 of the absolute value of x is 0. We did that one before. And limit as x goes to 0 of the constant function 0 would definitely be 0. So that gets me not what I want yet. That gets me the limit as x goes to 0 of this middle function, which isn't cosine x but is 1 minus the cosine of x. We get that this thing equals 0. Okay, so I'll use my my formulas for my limits, my laws, not formulas but laws, and I'm going to use the difference law. I know that since 1 is a constant function, I know that that answer is always going to be a 1. minus the limit as x goes to 0 of cosine x must equal 0, because that was what I proved. Doing a little manipulation, moving this guy over to the other side, I'll get the limit as x goes to 0 of cosine x is indeed 1. It was not straightforward, but we got there through the back door. Alright, we're going to try to use a squeeze theorem to show that if I was given this function x squared times the sine of 1 over x, and I wanted to know the limit of that function as x went to 0, what that equaled. I'm going to verify, or I'm going to prove to you, hopefully so, that that limit equals 0. I know right away that the sine function, sine of any theta, is in between a -1 and a 1. So I know that right up. I'm going to just let my theta equal some 1 over x, and I really don't care what he is. So I'm sitting here with this case here. Now what if I went through and just multiplied everybody by x squared? Because I can do that. So I get negative x squared here. Okay. Oh, that looks a lot like what I got. And let's say that I looked at the limit as x goes to 0 of negative x squared. That's a polynomial. I can plug that in. That limit equals 0. And let's say I look at this. Woo! Fix that. X squared. I can plug that in because that is also polynomial. There we go. That must mean that this function that is entirely in the middle, his limit is also 0. What is sneaky and not at all obvious way to get there. But it sure did, using that squeeze theorem, didn't it? Oh wow, and I guess that's it for section 3. This one was a little bit longer than the others. Now if you have any trouble with this, be sure and send me an email.